Starting with our Mastering Physics assignment here, we first have a position versus time graph showing a bicyclist, and we want to first find the velocity of the bicyclist at 10 seconds. Right here, we keep in mind that velocity is slope on a position graph, so what we're really trying to do is find the slope from here to here. So I'm going to pick points here. We have 0, 50, and we have 20, 100. So my slope is going to be change in y over change in x. So we have 100 minus 50 over 20 minus 0, which ends up being a slope and therefore a velocity of 2.5 meters per second. Moving on to part B here, we're just going to make it a little bit smaller. We want to know the velocity at 25 seconds, so that is right in here. Once again, that is going to be the slope. This one we don't even need to calculate though, because the slope at 25 seconds is 0. There is no slope, that's a horizontal line, so our velocity is simply 0 meters per second. Okay, and then for our last one, what is the velocity at 35 seconds? Okay, so we're over in here. Once again, we're going to calculate our slope. So I'm going to pick points. We have 30, 100, and 40, 0. So I'm going to say slope is change in y over change in x. So it's going to be 0 minus 100 over 40 minus 30, which gives me a slope there of negative 10 meters per second. For this next one here, this problem starts out by having this tactics box that helps kind of lead you through the problem. So we're just going to skip here to the actual problem. So the first question is asking us to simply find the position at 2 seconds, at 4 seconds, at 13 seconds, and at 17 seconds. So we're simply reading the graph here, and we're going to enter our answers separated by commas to 1 sig fig. So at 2 seconds, I'm just going to read the graph, and it looks like it's in between 4 and 5, but closer to 5. So I'm going to say that my position is 5 meters for the first one. So that's at 2 seconds. And then at 4 seconds, that position is 7. And then moving up to 13 seconds here, that looks like it's in between 8 and 9, but closer to 9. So I'm going to say 9 because we want 1 sig fig. And then finally, at 17 seconds, we're all the way down here, and that position is 0. So there's part A. We're going to move on to part B now. Moving on to part B here, we want to find our velocity at 2, 4, and 13 seconds in meters per second, and same idea, we're going to express it to 2 sig figs. So at 2 seconds, we're finding the slope of this line from 0, 0 to 3, 7. So that is going to be the change in y over the change in x. 7 minus 0 over 3 minus 0, or 2.3 meters per second. 2.3 repeating, but 2 sig figs would be 2.3. Moving on to 4 seconds. So we're looking right in here. We see that that is a horizontal line. Right, our point here would be 6, 7. Right, so we could calculate it, or we could just know that it's 0 meters per second. To 2 sig figs, it would be 0.0 meters per second, and that's what they want. So we'll stick with 2 sig figs. And then for that last one, at 13 seconds, I'm looking in this region of the graph here. And so I'm going to pick my points here. So we have 11, 10, and we have 16, 7. So same thing, change in y over change in x. And we end up getting 7 minus 10 over 16 minus 11. Okay, which ends up being 0.60 if we're doing 2 sig figs. All right, and for our last part, C, we need to put these times we're given into the appropriate category that describes the motion at those times. So Let's take a look here. Let's start with 2 seconds. So 2 seconds, we have a positive slope here in that region, which means we are moving to the right in the positive direction. At 4 seconds, we have 0 slope, which means we are stationary, so that's going to be in this category. At 14 seconds, that's the next one I have. That is in this region here with a negative slope, which means we're moving to the left. At 11 seconds, that is this point right here, and that's actually a point where we are turning around. We're going from a positive slope to a negative slope, so that is a turning point. At 16 seconds, right in here, okay, although we have a corner point, we're just going from traveling negatively at one speed to traveling negatively at another, so that's going to be a moving left point. And then at 9 seconds, which is right in here, we have a positive velocity, positive slope, so that's moving to the right. Moving on to our next problem here, we have a velocity versus time graph for Carl Lewis, the Olympic sprinter, while running a 100-meter dash, and we're asked to estimate his acceleration during each of the intervals listed, A, B, and C. So we instantly should be thinking about the fact that acceleration on a velocity versus time graph equals the slope. So that's what we're ultimately going to have to calculate. So for that first segment, I'm going to pick some points here. So we have 0, 0, and we are going to have to estimate a little bit. I'm going to say this point here is 1, 5.5. Those points are obviously estimated there. We're clearly a little bit less than 1, and the 5.5, I know that I'm more than halfway, so more than 5, but obviously not quite at 6, so we'll call it 5.5. There's going to be some leniency here on the answer. So those are my points. I'm going to go ahead and find the slope now. So for my slope, it's change in y over change in x, so 5.5 minus 0 over 1 minus 0, giving me a slope of 5.5 meters per second squared. For part B, I already have one of my points. I'm going to estimate my next point, this one here. I'm going to say that point is about 2.4. I think it's a little bit less than halfway. And for my velocity value, I will say it is 9.5. Again, it looks like it's more than halfway between here and here, but obviously less than 10. So I'll say 2.4 and 9.5. So I go ahead and calculate my slope, which is my acceleration. So it's going to be change in y over change in x, and so I get 9.5 minus 5.5 over 2.4 minus 1, which ends up giving me an answer of 2.857, which rounds to 2.9 meters per second squared, if I'm only doing 2 sig figs. For the final part here, part C, I need one more point, so I'm going to estimate this one. I'm going to say, again, I think it's about 3.4, looks like a little bit less than halfway. And for my y value, that looks pretty close to directly in the middle. So I'm going to say that is a y value of 11, because we're in between 10 and 12 here. So I'm going to go ahead and calculate my slope once again. So it's going to be 11 minus 9.5 over 3.4 minus 2.4, which ends up giving me a slope here of 1.5 meters per second squared. And we look at it just from its appearance. A is clearly the greatest slope, then B, then C. All right, moving on, we have another velocity versus time graph. We are told some important pieces of information here at the top, mainly that at time t equals 0, we're assuming the particle's at a position of 0. And the reason why that's important is in this first question, we're trying to figure out what the particle's position is at t equals 1. Now, you know from our lab that you can't determine position directly from a motion graph. All we can determine is the change in position or displacement. So in order to figure out where we are, all right, we have to know where we started and what the change was. So let's start with that. Okay, so we're going to find our displacement from 0 seconds to 1 second, which is simply going to be the area here. So it's a rectangle, so area is base times height, or 1 times 4, which gives us an area of 4 meters, and that is our displacement. Now, what is our position? Well, we have to think back to the fact that we started at a position of 0. So if we imagine a number line here, we're starting out here at a position of 0 meters, and we have a displacement, a change in position of a positive 4 meters, which means we travel 4 meters to the right. So that puts us at an overall position of 4 meters. For this problem, it really doesn't matter since we're starting at a position of 0, but in future problems, we might not start at a position of 0, and that would change our answer. So our answer here is simply just going to be 4 meters. We start at 0, move 4 meters to the right, so our new position is 4 meters. What is the particle's velocity at 1 second? Well, we're looking at our graph. We're now going to read our graph, right? For the first one, we found the area. Now we're going to read it. And so we see here at 1 second, we have a velocity of 4 meters per second, which is just a coincidence. That's the same as our first answer. What is the particle's acceleration at 0 seconds? We know that that is going to be the slope. So we're finding the slope of this line here, all right, which is going to be 0. All right, that's going to be our acceleration. So we don't actually need to calculate that because it's a horizontal line. We know the slope is 0. Moving on to part D here, we now want to find the particle's position at 3 seconds. So that would be the area from here to here, so this entire portion. What I'm going to do is I'm going to break this up into a few different areas. So I'm going to look at this rectangle here, call that area 1. This little triangle here, I'm going to call that one area 2. And then this rectangle down here, which I'll call area 3. There are a few other ways of breaking it up, but that's the way I'm going to do it. So we're going to find the area for each one of those. For that first one, it's a rectangle, base of 2, height of 4, so the area is 8 meters. That second one, this triangle right in here, so the area is 1/2 base times height. Base is 1, height is 2, so it's an area of 1 meter. And for that final one, that rectangle there, a base of 1, a height of 2, so our final area is 2 meters. So that means that overall our displacement from 0 seconds to 3 seconds is 11 meters. And since we started at a position of 0 meters, our displacement simply is our final position. We start at 0, we go 11 to the right, and so our final answer there is 11. Okay, moving on to our next, or last two parts here. We want to know what is the particle's velocity at 3 seconds. So velocity, we are simply reading the graph yet again. And so that is going to be at 3 seconds, we go up and it's 2 meters per second. And then what is the particle's acceleration at 3 seconds? Well, that is going to be slope. So I'm going to pick some points here. We have 2, 4, and we have 4, 0, and I'm going to find that slope. And so I end up getting that my slope, which is my acceleration, is -2 meters per second squared. All right, for the next one, we have another velocity versus time graph. And so our first question is, what is the object's position at 2 seconds? Yet again, we can find the displacement, the change in position from 0 to 2 seconds, and because we're told right off the bat the initial position, we'll be able to get the final position. Right? If we know the initial and the change, we can find the final position. So I'm going to break that area up into a rectangle there like that, and into a triangle, and get the area of each one of those. So the area of that rectangle has a base of 2, height of 4 is going to be 8 meters. The triangle has a base of 2 here and a height from 4 to 12, so a height of 8. And that gives us an area then of 8 meters as well. So I know that my change in position is that full area, which is 16 meters. So let's think again about our number line. Imagine we start at a position of 13 meters, that's what we're told, and we travel to the right, our change in position is a positive 16. We're going to end up here at 29 meters, and so that is our answer, 29 meters. For the next part, we want to figure out the position at 3 seconds. So what I'm going to do is, rather than starting from the start again, I actually know where I am at 2 seconds. I know that right here my position is 29 meters. So I'm simply going to find this little area, that triangle there. And that's going to tell me my change of position. I can get my final position from that point. So that little triangle has an area of 1/2 base times height. My base is 1, my height is 4, which means for this little segment here, from 2 to 3 seconds, my displacement is going to be 2 meters. So since I know that I was at 29 meters, my displacement is a positive 2 meters. My change is a positive 2, is really what that means. My final position will be 31 meters. Okay. I could have gone from this initial 13 and found the entire area of that triangle, but since I already knew where I was at 2, I only found that little extra bit. But either way would work. For the last part, we now want to find the object's position at 4 seconds. So what I'm going to do is basically the same thing. I know at 3 seconds I was at 31 meters. So I'm going to find my change, find my displacement for that little triangle there below the x-axis. So for that little portion, I have an area of negative 2 meters, right? My base is 1 second from here to here, and my height is negative 4. So I have a displacement of negative 2 from 3 to 4, which means that my position now at 4 seconds, considering I started at 31, is simply going to be 31 plus negative 2, or 29 meters. And that makes sense if I look at my graph visually, because I was at 29 here, and these two areas, those two little triangles, have the same area, but one's positive, one's negative, so they're really going to cancel out, okay, and give me the same displacement that I had, or same position that I had at 2 seconds. Last two questions here. One is a conceptual one. Does the car ever change directions? So I'm thinking here about what that looks like on a velocity versus time graph. I know that changing direction simply means that the sign of my velocity changes. And on a velocity graph, that means going from the positive area above the axis to the negative area below the axis. And that does happen right at this point here. So do we ever change directions? The answer is yes. And it occurs at 3 seconds, where that graph crosses the x-axis. All right, my next question here, we have a multiple choice question, and we have 3 velocity versus time graphs that we can see here, showing 3 different people, Andy, Betsy, and Carl. And what we want to do is determine which car has traveled the furthest at 5 seconds. So on this graph, we are looking for area. Okay, they're having a race. Which one traveled the furthest is going to have the greatest displacement. So I'm thinking about the area of this shape. Okay, so the area under the curve here, the area under the curve here, and the area under the curve here. Well, I see that they all get to the same spot. They all start with the same velocity. They all start at 0, and they all end at 40. But how they actually get there, the path they take, is slightly different. One has a curve going up, one has a curve going down, and the other is a straight line. So here's what I'm going to do, is I'm going to draw that straight line on each of these graphs, just for comparison purposes. And when we do that, we can see that Andy, this first car, clearly has less area because it's missing this section here. Betsy, though, clearly has more area than that straight line because it has this additional sliver above that line. And then Carl just is the straight line. So which one travels the greatest area? That's going to be Betty. All right, for this final problem here, we first want to draw the position versus time graph that matches the given velocity one, and we are actually going to have to do a little bit of math here. So what I'm going to do is I'm going to add in that graph and kind of show you step by step what we're doing to create that graph. So when you go on Mastering Physics, you should have a screen that pops up like this that allows you to actually create that graph. And the first thing you're going to do, just to get started, is we're going to add a line to it. And so you're going to click this Add Graph button, and it's going to pop up with this box here, and we're going to select a position versus time graph. And what we're ultimately going to do is we're ultimately going to click on that initial point where we want to start the graph from. And so that point is going to be the origin here, because it tells us that our object starts at a position of 0 at time t equals 0. So we're going to add in a line and just click that very first point on that line, which is the origin right here. So when we do that, we get this line starting with this point here, and it just goes directly across. We won't worry about that too much now. But we have our initial point there where that square is. So we're now going to start analyzing our graph. So we look at our velocity versus time graph. We see that there is a constant negative velocity. So we know that it's going to look something like this, on our position versus time graph. Okay, constant negative velocity means we have a constant slope, so a straight line, and a negative velocity, so we're going down. We do need to take this a step further, though, because we have actual numbers on our velocity graph. So we need to be more specific than just a downward sloping line. So what I'm going to do is I'm going to figure out at 4 seconds here, that's when we change velocities, I'm going to figure out what my position should be. In order to do that, I'm going to get the area of this rectangle here, because that's going to give me my change in position, my displacement. So I know that my displacement, when I find that area, all right, the area of that rectangle with a base of 4 and a height of -3, my displacement ends up being -12 meters. So that means that this graph at 4 seconds is going to be down here at -12. So I'm going to add in that point for -12. And the way I do that is I click this Add Point button, and the cursor will pop up, and it actually shows the coordinates. And I'm just going to go ahead and click that point for -12. And when I do that, I end up getting a line that looks like this. Okay, so now we have the graph correct up to 4 seconds. I'm then going to look at the next section of the graph, and this is a constant positive velocity. So I know my graph from 4 seconds to 6 seconds is going to slope back up. All right, constant velocity being a constant slope, so no curves on my position graph, and positive being a positive slope, so going up. But once again, I'm going to need to calculate the area of this rectangle here to figure out exactly where it's going to end up. So I find that that area of that rectangle with a base of 2 and a height of 3 is 6 meters. And so that means that I'm going to go from this -12 here up 6 meters, okay? And I'm going to end here at the point 6, -6, because my change in position was 6 meters, and I started at -12. So I'm going to go ahead once again and do Add Point, and I'm going to add that point in. So there's the next segment of my graph, and now I have one final segment here from 6 seconds to 12 seconds. Okay, I'm once again going to calculate the area of that rectangle to figure out how my position is going to change. So that rectangle has a base of 6, height of 1, meaning that it's a displacement or change in position of 6 meters. So I'm starting here at 6, okay, and I'm going to go up to at 12 seconds. All right, I'm going to have a change in position of 6 meters. Since I started at -6, that's going to bring me up here to 0. And so that's going to be my final point, is 12,0, because I know from 6 seconds to 12 seconds, my change in position is 6 meters, bringing me from -6 up to 0. And so when I go ahead and click that final point, I end up getting a graph that looks like this. Question B simply asks, what is the object's position at 12 seconds? Well, that's easy now that I've created my graph. I'm just looking right here at that point, and I can see that its position at 12 seconds is 0 meters.